Good day, everyone. This is Chris with the Ancient Scholar, and today what I'd like to do is I'd like to talk about a couple of experiments. Maybe I'll do one now, and then maybe dedicate a video per experiment. We'll see how things go. But I'd like to talk about how we kind of came, what our humble beginnings were to chemistry, and to figuring out that there was more to the atom than we initially anticipated. I'll try to keep the math down to a minimum, because really what I want is a good conceptual, visual understanding of what really led people to start thinking about chemistry, and obviously physics is what we ultimately use to explain chemistry, but what really led us, or what forced us to really think about these non-intuitive ideas that we currently use to describe the universe, and we're still currently trying to figure out what some of these fundamental ideas, if some of these ideas really work, and how can we test them. And obviously there's a whole lot of discussion going on because of some of the exciting news that's come out of the Large Hadron Collider, and we have various theories. And if any of you are old enough, at least in your 30s and beyond, you may remember, if you're really scientifically oriented, you're interested in science, you may remember that it really wasn't until the late 60s, early 70s that some of these I suppose radical theories, if you will, started coming out about strings and membranes and whatnot. Well, I think the idea of more than three dimensions of space has been around for a while. Back to the time the early 1900s, when we're talking about relativity and alternatives to relativity theories. Extra-dimensional theories have been around, but really we didn't start entertaining them seriously until at least into the 70s. Late 60s, early 70s, we had people that were kind of using string theory, and actually string theory came about. It had really humble beginnings, and it was used. They were trying to describe particles that were composite, or particles that were made of other things, like protons and neutrons that that appeared to have something else to them, some other structure. They weren't fundamental. And as I understand, the string theory and all this was actually initially a theory of hadrons, or large particles with quarks in them, and we realized that perhaps it could be used to explain things like gravity and so on. And obviously that's from there it's become very popular, all the different types of theories out there, and we really have very non-intuitive ways of looking at the world now. And kind of get back to the original subject, I wanted to go ahead and just talk about some of these key experiments that were done that really demonstrated pretty definitively that something was very different than we always thought. So what I want to do is I want to talk about the atom. And we've long suspected, at least as far back as Greek philosophers in Greek philosophy, that if I take something, an apple or an orange or a piece of bread or what have you, and I cut it up, I can cut it into smaller and smaller and smaller bits. And the Greek philosophers thought about this, and they thought, well, eventually, if I could keep cutting something up, could I get to some fundamental bit that I really can't cut down anymore? There's just a fundamental building block that's all there is. That's as small as it gets. And that's it. That's the definitive building block of everything. And of course, that's kind of where the term atom comes from. It means indivisible. That it's an indivisible little building block. So the idea of some fundamental thing, block, atom, if you will, a building block of matter, of larger things like molecules and cells and so on, has been around for a little while. And from the ancient Greek philosophy, we had the European Renaissance. Of course, Newton really enlightened us to classical mechanics, and Maxwell came along and enlightened us to electricity, magnetism. And right around the late 1800s, after all these classical theories were well established, our idea we knew about atoms, or we knew about elements, and we suspected that the elements were generally these indivisible building blocks of chemistry. We didn't really think that atoms had any structure to them. I'm sure some people thought about it, but the general way of thinking about it was, nah, that's just a fundamental thing. So the first kind of experiment that I want to talk about, and I'm sure there were others, but this is kind of a profound experiment, was done by a physicist, J.J. Thomson, in the late 1800s, in the Cavendish, I believe it was in Cavendish Laboratories, so this would be in England. And what he did is he took an element called hydrogen, and we know hydrogen's a pretty simple element, and what he did is he kind of took hydrogen and put it in a cathode ray tube. In this tube, and what I'll do is I'll just kind of draw what we have inside of this tube here. So we have maybe something that kind of looks like that, and then something that kind of looks like that. And let's just assume that obviously it's encased in glass or what have you. And what he did is he put a potential. Okay, so I put a potential across that, and so I have negatives, a lot of electrons here, not a whole lot of electrons here, and obviously we didn't know about electrons then, but we were soon to know about electrons. But he put an electricity potential across that, and then I have all this hydrogen gas in here. Okay, put a potential across this, and the gas started to glow. Okay, so I started to get light glowing from that. Well, that isn't particularly exciting. We knew that that happens, and we didn't exactly know what was going on, but J.J. Thomson decided to take this a little bit further. And what he did is he took two plates. Okay, so I'm just going to draw a plate here, and I'm going to draw a plate down here. Okay, just like that. And he put a charge on these plates. One plate had a positive charge, okay, and one plate was negatively charged. So, he put electrical potential across those plates. And then he kind of had a screen, a phosphor screen back here. Okay, a phosphor screen back here. And then what he did was something really interesting. He poked a little hole, tiny little hole in this tube, and allowed whatever that glowing stuff in there was, allowed a thin beam, a thin stream of it to escape. Now, the traditional, conventional way of thinking was that that beam would just shoot straight onto the phosphor screen, and I'd have a bright spot where that beam hit. Okay, that would be a traditional way of looking at it. Well, something rather interesting occurred. And what happened was, well, there are several things that happened, but I'll talk about the really interesting thing here, was that the beam didn't go all the way straight forward. Part of that beam kind of broke off like this and hit up here, okay? And it moved toward the positive plate there, okay? It moved toward the positive plate. And what we realized from this was that this gas, this plasma, okay, from putting electrical potential across hydrogen gas, in this gas there was more than just hydrogen, okay? There's something else, and there's something else that was attracted to this positively charged plate here, because part of that stream, those particles in that stream moved up toward it, and the other particles moved forward. And there's actually a tiny, tiny, tiny little bit that, of course, moved toward the negative, and we'll talk about that as well. Well, what do you suppose is going on here? Well, what J.J. Thomson realized was that the atom was not composite. The atom wasn't a singular entity, and that somehow putting the electrical potential across that hydrogen excited whatever the stuff was, okay, whatever the stuff was that made the hydrogen atoms the composite particles, or whatever, the building blocks of this. It excited them, and this beam was basically a soup of all of these different building blocks of the atom, and those building blocks had charge to them. Okay, some of them were attracted, some of them were attracted to the positive plate, some of them attracted to the negative. So it would be safe to assume that this is just a tiny little movement, but a large portion of that beam that was hitting the phosphorus screen, the angle was bigger here, was moving up toward the positive plate. So it was safe to assume that whatever that component of the hydrogen was, it had a relatively small mass. Okay, it had a small mass, and it was easier. It had an easier time, if you will, moving toward the positive plate. Whereas whatever this other thing was, that was attracted to the negative plate, probably had a larger mass. Because it didn't move as much. And obviously that was a pretty safe bet, and it turned out to be the case. But really what this fundamentally changed our way of understanding, the way that it did was, this was the first time that we realized that atoms were composite, they were made of more fundamental things. And really what this signified was, this was the discovery of the electron. And those particles in that plasma that were attracted and moved toward that positive plate were electrons. And obviously the smaller part of the beam that was attracted to the negative plate were protons, and it took a while to figure all that out, but really this was the fundamental discovery of the electron. And that really led into, okay, now we know that the atom is composite, it's composed of different particles, and now what we need to do because of this experiment from J.G. Thomson is we need to figure out how all that stuff is arranged in here, right? Just like if I drive a car, most people are not necessarily satisfied that you have a car and it drives. You want to know what makes a car tick, right? You want to know where the what is a carburetor, where is it? You want to look at your car or a machine or whatever, and you want to figure out what the sub-levels of structure are, because that's obviously, when we talk about cars, it's very helpful because we can modify, manipulate, and fix and do different things. Well, the same thing is true with the atom. If we figure out what the structure of the atom is, perhaps we can use that knowledge to our advantage, and we definitely have over the years. Okay, guys, I'm going to go ahead and cut it off here. Hopefully that made sense, and hopefully it was fairly intuitive. And we will move on and talk about a couple of other experiments in subsequent videos. As always, thanks for hanging in there, guys.